Thank you very much for the opportunity to speak here. I'm Sepehr Nezami from Stanford University. I'm going to talk about this work, Continuous Symmetries and Approximate Quantum Recursion, which is a joint work with wonderful collaborators, Victor Albert, who is sitting there, Philip Feist, Grant Salton, Fernando Pasowski, Patrick Hayden, and John Presco. So let me start. I'm going to focus on two fundamental concepts, quantum recursion and symmetry. And I'm going to explain that there is a conflict between these two. And my goal in the next 30 minutes is to formalize and understand this conflict in details. So let me start with motivations and definitions and tell you what my setup is. The quantum recursion setup is an easy one. So you have a logical Hilbert space, you have an isometric encoding, or you can have a non-isometric encoding as well, but for this talk, you can imagine that you have an isometric encoding of the logical Hilbert space to a physical Hilbert space containing of n subsystems. And here I'm going to focus only on erasure correction of a single qubit or a single subsystem. So I demand that my code be able to correct loss of one of these AIs. Then I have to tell you what I mean by a system that has symmetry and quantum recursion, and that's a notion of covariant codes. It's a central notion I'm going to talk about in the rest of the talk, and it's defined as follows. Suppose that you have a symmetry group G, and the representations of this group G acting on different subsystems, different Hilbert spaces of your system. So you can have a representation acting on logical Hilbert space or physical Hilbert spaces. And we say that the encoding is covariant with respect to this group G if you act by this logical, if you act by the group on the logical Hilbert space and then encode, it's going to be the same operator as encoding and acting by the group on the physical Hilbert space. In other words, covariance means that if you rotate and encode is same as encoding and rotating. And it's important for me that this physical physical representation is a tensor product of representation, but we can also relax that to contain cases like overlapping generators or non-local Hamiltonians. But for now, we can focus on tensor product representation on the physical Hilbert space. Why do we study these things? Why we care about them? One reason is that they come up in many different scenarios. One of them is reference frame quantum recursion, when you have two parties, Alice and Bob, that do not share a reference frame, meaning that they are unaware of each other's relative orientation in space, but still Alice wants to send some directional information through a noisy channel to Bob, such that Bob can recover the spin or the stick pointing at exactly the same direction as Alice's. Because it's a noisy channel, you want to use a quantum error correcting code, an erasure correction code in between. So Alice wants to encode her information, and Bob wants to decode that they still recover this, they point in the same direction. And you can see that this task cannot be done perfectly, and the reason, and you can see that also this problem is closely related to the question of whether there exists rotation covariant quantum error correcting codes. So these are mathematically the same problems. Another example happens in condensed matter systems, by, for example, the paper where the previous speaker was talking about is a co-author of. So you would like to encode your logical information in a narrow band of eigenvalue energy eigenstates. And you can see that in many cases, like the cases you have a complex Hamiltonian eigenstate thermalization, this kind of encodings of the logical Hilbert space to a couple of energy eigenstates is going to be a good quantum error correcting code, a good approximate quantum error correcting code. And this kind of codes also have a symmetry, which is the time evolution. It's a Hamiltonian evolution. Another two examples are holographic duality and fault-tolerant quantum computation, but I'm going to spend more slides on. So let me start with holographic duality. Again, the setup is a common ADS-CFT correspondence. When you have a higher dimensional gravitational theory, it's quantum gravity in the bulk. You can think of it as the soup inside this cylinder, which is dual through this magical ADS-CFT correspondence to this conformal field theory, non-gravitational theory on the boundary of the cylinder. And this duality means that whatever happens in the bulk or corresponds to something that happens on the boundary, and anything that happens on the boundary corresponds to something that happens in the bulk. So there is an actual duality. And in particular, if you act by some operator in the bulk, there is a corresponding operator acting on the boundary. You can ask where this operator acts on the boundary, and to answer that question, we have to define this notion of entanglement wedge of a CFT. So here, the boundary is your conformal filter, it's a time slice. And consider you have a region A, suppose that you have an interval A on the boundary, and this interval A has two ends, so you can connect it. And the region between A and this line, this geodesic between two ends of this interval is called entanglement wedge of this region A. And there is a fact in a CFT correspondence which is called entanglement wedge reconstruction, that tells you that if you have an operator acting inside an entanglement wedge, like here, it can be reconstructed under region A. So this point has a dual only on A. This would, as observed by Almeri, Dong, and Harlow, would lead to quantum error correction. Why? Suppose that this is still the same time slice, and you have an operator acting in the middle of the bulk. And consider these three intervals on the boundary. Because of this entanglement wedge reconstruction, the mapping that maps operators in the middle, which we can look at as a logical Hilbert space, to the joint region A1 and A2, because this point is in the joint entanglement wedge of the A1, A2 boundary region. So this can be reconstructed on A1 and A2, which means that you can correct the erasure of subsystem A3 on the boundary. And A3 is not specific, so you can correct the erasure of any one of these A1, A2, or A3 subsystems. So meaning that if you look at this point, or the operators in the middle as a logical Hilbert space, that's going to be mapped to the boundary, this mapping is itself a quantum error correcting code. And this, again, has a symmetry, which is time evolution symmetry. So you can map to the boundary and time evolve, or you can time evolve and map to the boundary, and it should give you the same answer. So this is another application. And the last one is probably most important one for us is Ising-Kinel theorem. So suppose that you want to do quantum computation, and you ideally may want to have these two conditions for your encoded data. You would like to be able to correct the erasure of a single subsystem, because that would be nice if you have a good quantum error correcting code. And then ideally, you would like to be able to transversally implement any logical unitary, meaning that you want to be able to implement any unitary on the logical Hilbert space by tensor product operators. If you can do that, it's nice, because then the errors in one subsystem will not propagate to other ones. But Ising-Kinel showed that there is no code with these two properties. And in fact, they showed something stronger, that there is no exact quantum error correcting code with a continuous symmetry. So there is a no-go theorem. And the perspective we're going to take here is that we do not need necessarily perfect codes, and we're going to understand approximate quantum error correction and understand approximate versions of Ising-Kinel theorem and their applications. So let me go to the main question I'm going to ask: when do covariant codes exist? I'm going to answer this question by just looking at different scenarios. I'm going to look at the cases when you have a finite dimensional coded space, you have an infinite dimensional coded space, or you have a finite symmetry or continuous symmetry. And you can see that for the cases you have a finite symmetry, finite dimensional coded space, and continuous symmetry and infinite dimensional coded space, you can actually construct codes that are covariant and error correcting. And we have these nice constructions based on the regular representation of the group. So therefore, the size of the Hilbert space is going to be the same as the size of the group. The dimension of the Hilbert space is going to be the same as the size of the group. But for the rest of this talk, I'm going to focus on this regime of conflict when there is, you know that there is no perfect code by Ising-Kinel theorem. So we're going to study approximate quantum error correction. And we can actually study the approximate symmetry as well, but that's in the paper. What I'm going to focus on approximate quantum error correction here. And what I'm going to do is that we can prove a stronger upper bounds on the quality of this code. We're going to say that, okay, if the code has some covariance conditions, has some symmetry, then it cannot be perfect. So we're going to prove some bounds on those kind of the quality of this code. So we're going to prove approximate versions of Ising-Kinel theorem and provide high quality symmetric codes. So before going into details, I'm going to just quickly and intuitively tell you why Ising-Kinel theorem holds. The reason is that the Lie groups have generators, just Lie algebra elements that are called charges. So you can write any, so you can think of it as a U1 subgroup of your favorite continuous group. And the fact that the code is covariant with respect to this generators, with respect to this group, means that the charge is conserved, meaning that if you look at the expectation value of this charge generator, the generator of Lie group in the logical Hilbert space, so TL expected on the logical Hilbert space, is going to be same as the expectation value of the charge operators on the physical Hilbert space, the physical charge on the physical Hilbert space. And you can see that interestingly, this physical charge is sum of different elements. And this immediately tells you why you cannot have perfect quantum error correction, because you know that if you have perfect quantum error correction, then individual physical subsystems should contain no information from the logical Hilbert space, meaning that the individual density matrix, local density matrices should be totally decoupled from the logical Hilbert space, which means that this. But these terms, this T1 physical, this expectation value of these charge operators can be evaluated locally. So these terms should individually be independent of the logical state. But because of charge conservation, this means that TL logical should be independent of the logical Hilbert space, but that's wrong, because you can just change your logical state and go to different charges. In other words, this charge conservation tells you that the information about the charge value will necessarily leak to the environment. And that is what's preventing you from having a perfect quantum error correcting code. So now I'm going to expand on these ideas and go to the approximate versions, approximate cases. First, I have to tell you what the figure of merit is. It's not really important what we choose. Here I'm going to focus on worst case entanglement fidelity of recovery, but you can look at it just like ordinary entanglement fidelity of recovery as well. It's defined as follows. Suppose that you have its encoding, you have the noise, and you have the recovery channel. So you get this combined channel, and you feed in some state between some entangled state between logical Hilbert space and some reference system. And you look at the fidelity of this state in the input and output. You choose the worst possible state that gives you the least fidelity. So it's called worst case scenario. And then you're going to optimize and choose the best possible recovery channel. And you get this fidelity. And I'm going to look at this quantity epsilon is equal to square root 1 minus fidelity squared. If you didn't follow this, basically what you have to remember is that if epsilon is 0, you don't have a perfect code. If epsilon is large, you have a bad code. So that is my figure of merit. And now I have my first bound. The first bound lowers bounds epsilon. The fact that it's lower bounds with non-zero elements means it's Sinkinel theorem, because it means that you don't have perfect code. But let us look at this elements that go to this bound. One of them is 1 over n, is number of subsystems. So bound gets weaker when you have more subsystems. And the other one is delta Ti. Remember that delta Ti's are generators, or just charge and generators of the Lie group. And delta T means delta for me means the difference between maximum and the minimum eigenvalue. It's 1/2 the operator norm. And you can think of this delta TL be fixed. So basically, if you have larger physical charges, then you have better codes. You can have better codes. The bound is weaker. So let us study these two scalings. So there is the question of why large n helps. It's easy to understand intuitively, because we know that the thing that prevents you from having perfect code is leakage of information about the charge value to the environment. But if you have more environment systems, then going to be less information leaking to each one, which gives you potentially better codes. And you can basically construct these codes in the same paper that I mentioned before, that you map 0 logical to states with the fixed Hamming weight M0, and 1 logical to a state with the same superposition as state with the fixed Hamming weight M1. And you can see that if you construct codes like this, then the error scales as 1 over n, and still this is covariant with respect to the total spin or total magnetization. So you can construct codes with the same scaling. The next part is more subtle, that why larger physical Hilbert spaces can help. And so for this case, we have codes here, which are basically generalization of this 3Q3 code, but we go to Z instead of Z3, and we put a Gaussian envelope. And you can see that these codes have scaling similar to this, not exactly the same, but very close to this scaling of this bound. And I think the intuitive reason that why larger physical Hilbert spaces help is that if you have more space available, you have more space to hide your charge value. Basically, what matters, what prevents you from having a perfect code is that expectation of charge value, expectation of TIs will change, but quantum recursion is sensitive to fidelity. It's only understands the fidelity. So when you have more physical Hilbert spaces available, you can have two states which are very close in fidelity distance, but they have very different expected value of the charge operators. So that might be their explanation. And so you have this kind of, we also want to just, I'm going to mention that this work by Alvar Alhambra and Misha Woods, that they give constructions of good high quality U1 covariant codes using reference frames and clocks. And these constructions are nice. So suppose that your symmetries are time evolution. So this basically covariance means that it doesn't matter when you encode. You don't have to record the time of the encoding. Any time that you act, it's going to give you the same final result. So now, so far I was talking about U1 codes or U1 subgroups of the non-abelian groups. But the bounds get way stronger when you go to the non-abelian case, when you actually use the non-abelian structure of the groups. And interestingly, the bounds in these cases can be written in terms of dimension of subsystems, not the size of generators. It's more like initial information for us. And there we can prove approximate East-Inkinol theorem. So first, recall that for U1 codes, you can basically multiply, you can scale your generators by any number. So this ratio of delta TL or delta TI is free. If something is a representation of, say, R or U1, if you multiply it by 100, it's going to be still a good representation. But for UN, for non-abelian groups, it's not true. So for example, consider the case of a U2 group. Now the group is SU2 or U2, and you know that the generators of SU2 are spin J representations that have a spin going, that for example JZ has elements J over 2 to minus J over 2. So, and then for this case, you know that delta T, the difference between maximum and minimum eigenvalue is J, while the dimension is 2J plus 1. So now there is a relation between the size of the generators and the dimension of the Hilbert space. And you can write it in this way. So if I substitute it to my bound, I get this newer bound, which gives you that the error for SU2 covariant codes is lower bounded by 1 over n and 1 over dimension of the physical Hilbert space. So now this is a nicer bound. And just to remind you what the setup is, I have a two-dimensional logical Hilbert space, and I have a code which is covariant with respect to the U2, with all logical unitaries in this logical Hilbert space. So the new bound is in terms of dimensions. But things are going to get exponentially better, way better when you go to the larger logical dimension, and this is where things get actually very interesting. So for this is a slide for if you remember this weight diagrams from representation theory books. So the first one is you know that the weight diagram of U2 is just basically a line. So delta T is the difference between maximum and minimum eigenvalues, and number of each point can represent at least one Hilbert space basis element. So this is a number of dimension of the Hilbert space. So you know that delta T is going to grow as dimension, number of points. But if you go to U3, then you know that the weight diagram is a two-dimensional object. And delta T is going to be the width of this two-dimensional figure. So the number of points inside the dimension will grow by a square of delta T, which gives you the delta T, the size of this generator, going to grow by a square root of dimension. So this gives you much stronger bounds. It gives you epsilon. If you look at this previous slide, which was 1 over D, now this gives you this epsilon lower bounded by something like a square root D, which is way stronger. And in fact, if you go to very large dimensions, the weight diagram is something like DL minus 1 dimensional picture, which gives you epsilon, which is lower bounded by 1 over di, the physical dimension, to the power of 1 over dl, which can give you a very, very small number. So it gives you a strong bounds. And if you do the math precisely, you get this interesting bounds. Just again to remind you what the setup is, I have this logical DL dimensional Hilbert space, and I'm considering the codes which are covariant with respect to this whole logical unitary group, meaning that if I act by a logical unitary, and encode is the same as encoding and acting by a tensor product operator. And these DIs are dimension of the physical Hilbert space. So let's go back to the bounds. So this is my main bound, which is slightly more complex. It's slightly complicated, so I'm going to look at 3 different cases. The first one tell me that the error is lower bounded by 1 over n again, and also 1 over number of physical qubits, log dimension. So this is way stronger. The second case, which these 2 cases are more interesting. So suppose that you would like to fix the error, aim for a constant error, epsilon, and then you would like to see, and you would like to increase the size of the logical Hilbert space. So this bound tells you that in these cases, the number of physical qubits divided by the number of logical qubits is going to be lower bounded by 1 over 2n epsilon. Meaning that if you aim for encoding 20 qubits into 3 subsystems and you want to keep the error as low as 1 over 1,000, then you need something like 2,000 qubits. This is a theoretical lower bounds for any code that you would like to make. And the last case is when you want to keep DL, the logical dimension time epsilon is small, and DL large. And in this case, you need exponentially many physical qubits. So the number of physical qubits should be exponential in the number of logical qubits, which is completely prohibitive. And so far, I've just given some bounds on this kind of codes, and I have not told you. I haven't mentioned any actual code. So the question is if such codes actually exist, and the answer is I can't prove them, but I cannot construct them. I can prove that they exist. And this is a very, very randomized construction. So suppose that you have, you look at the encodings, which are covariant with respect to the whole unitary group. And the representations I put here are E-reps of the unitary group given by these Young tableaus, lambda, mu, and nu. So something I do is I look at all the encodings which are covariant with respect to these representations, and I choose a random encoding. You may say that it's good, but it's not good. You also have to choose the Young diagrams randomly. So you have to choose random representations, and then you choose a randomized symmetry, and then you can see that you can actually construct good codes, good covariant codes, good quantum error correcting codes with a covariant with respect to the whole unitary group. And you get codes with this set of parameters, which basically tells you that if the number of physical qubits is large, then DL squared is the logical dimension times log 1 over epsilon should be large, meaning that 1 over epsilon should be large or epsilon should be very small. So you can get codes with very high quality in this way. And these constructions heavily rely on this kind of a modern results on representation theory of smoothness of Littlewood-Richardson coefficients that goes through this in this proof. So to end, we proved approximate versions of the async theorem and discussed the applications. We bound the recovery fidelity for approximately covariant quantum error correcting codes. We gave a stronger bounds for non-abelian cases. And we gave construction of codes with covariant with the whole. We proved the existence of the codes which are covariant with the whole unitary group. And importantly, our bounds work for the cases when you have overlapping generators like overlapping Hamiltonians and simple time translation symmetry. And with this, I think I would end.
Okay, we have plenty of time for questions.
What type of recovery operator do you use for the bound on the recovery fidelity?
Oh, you mean, say, Say here.
Yeah.
Yeah, this, I did not fix the recovery channel. I'm just like optimize over all possible quantum channels.
Okay.
Yeah, so this is a theoretical bound. It's not actual recovery. Actual constructive recovery.
I mean, how do you bound it? Do you like have some ansatz for the recovery channel, or do you?
Oh no, this is generic. This is totally general result. I can tell you this.
So as well as the Eastern nil theorem, there are other sort of hand-waving arguments people make for not being able to find continuous fault-tolerant gates for codes. And one of them would be that it's sort of become something similar to classical analog computation, which we know is not fault-tolerant. Another being that it's hard to distinguish infinitesimal rotations from local errors. So do those issues crop up in this research?
I think that's a very, very good point. I think one of the issues with these infinitesimal errors is when you don't want to necessarily correct for erasure errors. You want to correct for just small drifts and small errors. So somehow if you're covariant with respect to the discrete group, then that would naturally help you with correcting the small errors. And here is kind of an open question. Oh, I'm going to the wrong direction. So this is, oops, yeah. So this is kind of an open question they had here. Basically, we have to understand other types of errors. If this kind of constructions are useful for actual fault-tolerant quantum computation, I think you have to go to very large dimensions, like photonic systems or infinite dimensional systems. And there, I don't have a concrete answer, but I do think that you might be helped by this very, very large dimensionality of Hilbert space and the fact that it's very low probability that things drift in the same direction. But yeah, I think this is a very good and important question. We have to understand other types of errors. Yeah.
Hi, so I'm very new to this, so I have a very, very basic question. When you just said about bosonic systems where you have a larger Hilbert space and maybe you can apply this in those systems, a bosonic qubit is still a qubit, right? Like the GKP qubit is still a qubit. And so a follow-up question is that if, there were several proofs by Sergei Bravi and other people, I'm sorry if I'm forgetting the names, that they had more geometric arguments which did not actually assume any structure to the Hilbert space. They just said that if you have qubits with certain properties, blah, 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 you cannot, and if you have just locality constraints, then you cannot have universal fault-tolerant computation. So what would you like to say about that?
If I recall correctly, I recall this kind of arguments, and I think those are, well, what you're doing here is just basically providing a very strict lower bound for the codes, given the dimension of the Hilbert space, dimension of the, dimension of the physical Hilbert space. And I think if you consider more structure in your code space, like if you want the codes are going to construct on the lattice or something like that, I think you would get for sure better bounds. So. Yes, and for the bosonic systems, I think, for example, if you're looking at the GKP codes, then you have to consider a two-dimensional code. I mean, the system is essentially two-dimensional unless you play with that. Well, I don't know. Maybe we can apply this bounds in a non-trivial way there, but I don't see that now. Maybe Victor has a comment.
I had a comment on Ian Kai's question, how do we prove it? So we use Benny Oreshkov's trick to convert to complementary channel, which depends on this. So where the equivalent of the recovery depends on a particular state, we use the triangle inequality between sort of two two different input states to get rid of that state, and then we bound that using a particular operator that quantifies how much the environment is able to obtain from the code. And covariance of the code implies that the environment can obtain some information by locally measuring a particular sort of local charge, and that gives us the lower bound.
Yeah. So yeah. Thank you. So this is very important because we are using this Benioff-Reshkov result, which is very non-trivial. It uses this, to me, weird-looking min-max theorem. So it's a complex argument going there. I didn't explain that well. Sorry.
We have another question there.
So last year there was this paper by Oguri and I think Patrick
Harlow.
Daniel Harlow, right? About basically proving that you cannot have continuous symmetries in ADS-CFT due to arguments very similar to the Easton-Nil theorem. And I was wondering if your setup of approximate QEC can be applied to these setups.
Yes. So let me, if I can make this larger. From the current slide. Yes, so those results, I mean, it's a bit, that's a very good point, and I think there are a lot of details go there. So they use symmetry. So I talked about time translation symmetry, while ADS-CFT naturally has a lot more symmetries. Many of them are actual symmetries in the bulk and gauged in the boundary. Most of them are like that. And for those cases, you have to use this notion of asymptotic symmetries that Harlow and Oguri have, and they have an argument that looks like this one, but in fact, if you go deep, is completely orthogonal, and they use a lot of actual CFT physics type of ingredients going there. And one way to see that the argument is different is that the argument works for discrete symmetries as well, while for ADS-CFT that doesn't work. And basically, the argument, the quantum information part of their argument, I think, goes like, they show that eventually there is a logical and correctable subsystem that should be, therefore the logical liberated space should be somehow trivial. But yeah, and the reason I use time translation symmetry is because if you look at the actual gravitational picture, you have this nice Wilson lines, gravitational Wilson lines that are constructed by this energy momentum tensor going from the bulk to the boundary. And somehow these Wilson lines will overlap. Yeah, so so in some sense, they don't see these Wilson lines. The Wilson line is not a problem for them because they look at the symmetries, which are not in the sense of time translation or space translation symmetries. But here our argument works for all symmetries. So I'm specifically mentioning the regime where the argument doesn't say anything, while this generic quantum information setup is informative. Yeah, I can explain more, but yeah, thank you.
Okay, so if there are no other questions, let's thank Sepehr again.